Today I'm going to talk about the bias-variance trade-off in a regression setting with a squared error loss. My name is Santana. Before we actually discuss the perspective of bias variance from a machine learning algorithm point of view, let's just define a few terms with an example. These are shots fired in a gun range, which you see on the extreme right side, which I shamelessly took from my child's scout camp recently. What you see on the leftmost essentially is someone who is able to shoot pretty much close to the center, but only in terms of the average sense. He's all over the place otherwise, he or she. While the middle person seems to be able to shoot very accurately, but he's a little far away from wherever the actual center is. So what we're saying is, if this gap between whatever is the mean of the observations to whatever is the true mean is too far, this is what we call as a bias. In this case, the spread from whatever is the mean is too large, which is what we call as a variance. Let's drill down to some details. I'm going to assume x is the random variable, which represents the features of whatever is the experiment that we're going to conduct, and y is the labels for the samples. I is the index used for each sample, and I'm going to assume that capital N is the number of observed samples. What does any machine learning model do? The model would fit some function f to the input x. So in other sense, if you give the set of n samples that one observes or any estimator observes, the model would find out whatever is supposed to be the f. And after it finds the f, if you supply another new input, let's call that as xn plus 1, then the model is going to give you an output, which is the y hat n plus 1, and then you can compare it with whatever was the true value of yn plus 1. Let's try and understand how far the error between the true prediction, the prediction and the true value are. So before we do that, let's just get some questions in our head answered. The first point here that anybody would ask me is, what if you observe an infinite number of samples? That is, what happens if this capital N goes to infinity? When capital N goes to infinity, we assume that we have seen all the samples, or in some sense we've seen a very, very large number of samples, and by that time we will have complete information about the data's true distribution. But that's too ideal, let's just forget it. So let's come to reality. In reality, the capital N, which is the number of samples that anybody or any estimator would observe, is a finite number. What we want to believe here is, if this capital N is finite, then the same experiment could be replicated at multiple places, and simultaneously you can get two different estimators for the same problem. And we can understand how far these two different estimators are. That's basically what we're going to try and ask. Is that all the question that we have? We have another interesting question, right? The point here is, suppose, for example, if the true number of variables or the number of features was too large, but I was only able to observe a very small subset of variables, then whatever model that I would build will look very simplistic. The same way, if suppose, for example, there are two people or two estimators who are trying to find a model, and each one of them is observing a completely different data set, which means like my sampling is very, very bad. So in these kind of scenarios, we have some pathologies. So let's try to look at these with a specific example in mind. So the example that I have for today is to classify whether a single credit card transaction was fraudulent or was it legitimate. To do that, what all features would we typically use? We could use things like the actual amount of the transaction, what is the time at which it happened, how far away from the house, how many transactions happened, and the typical values which are like intuition driven, like if it happened in the middle of the night, then most likely, unless and until it was done by the person, it was bad, or if there were consecutively large number of transactions, then most likely it's a fraud. And the labels here would be whether or not it's a fraud. So the labels here are binary. Let's look at this example first. In this case, we want to understand whether these two realizations that are observed, let's call that on the left side to be dn1 and the right side to be dn2. Observe here that the blue transactions here are corresponding to the good ones. It so happens that you see a bunch of very, very, very small valued transactions. So the y-axis here is the amount of the transaction, and the x value here is the time at which the transaction took place. This is a distribution of a large number of transactions which have happened fraudulently but with very low value, while the second experiment or the second data set essentially corresponds to a bunch of fraudulent samples where all of them are very high values. This is basically the situation that we just started the discussion with. I don't even want to consider this. So what we're going to assume is that any realization that has been seen is very representative of what was a true value. So let's take this as an example here. So in this example, let's say, for example, let's say that dn1 is this data set where you have these white ones to be assumed as frauds, and the blue ones are essentially the true values. And the second realization says that there's this orange frauds and the blue ones are the true values. And similar to our intuition, most of these transactions typically would have happened late in the night or early in the morning, and most of them are typically of very high value. But it doesn't mean that any transaction of a very high value doesn't mean that it is actually a fraudulent one, right? So the first interpretation here is, if my model is really too simplistic, in the sense that, suppose if I was able to only observe the value alone and I wanted to build a model only based on the value, then what would happen here? So if I did that, so let me draw that picture here. So suppose I was just trying to choose what is the value and decide the label based on it, then I can basically sort of choose a threshold like this number for the first transaction, and the second one would have a threshold which would look like that. But for the prudent observer here, you could basically say that, hey, there is a possibility of actually finding this one common threshold for both of them, and it might most likely satisfy. What is this telling us here is the estimator that is built by looking at the set of observations dn1 and the estimator which is built based on the observations dn2 look almost identical to each other. In other words, both the estimators are almost behaving identically to any new data point that is going to come to me. So let's summarize that. What I'm saying here is that both the models, which is like the one using dn1 and the one that was using dn2, are simplistic, essentially, which means both of them are only going to be based on what was the value that was the transaction's values. Now, or the time of the transaction, whichever. So if you build a model which is very simplistic, then what typically happens is most models look almost identical to each other. But the advantage there is that irrespective of how the data varies, the model will behave almost identically. Let's look at the other extreme of the spectrum, which you would have guessed by now. The other extreme of the spectrum essentially is, I observe this, again, the same data set, but now I'm going to use both the variables to build some functional form. So I'm going to use both the value of the transaction and the time at which the transaction happened. So for the first transaction set, I'll build this function f1 of tv. For the second transaction, I'll build the second function, let's call that as f2 of tv. So if I build these two functional forms which are so specifically tied to this set of transactions alone, then what is going to happen in this scenario is I might pretty much be able to fit this current dataset dn1 so very well with fn1, and d2 will be fit perfectly using f2. What's the interpretation of this tight fit? The interpretation essentially is just that small variations in the input would actually sort of throw these models far off, which is very obvious, right? Because if this particular input was given to this model, it would declare it as a false one. The second thing is, the nice part on the other hand is, each one of these models is actually a good model. So if there was a possibility of actually averaging out all the models, then we might get a very, very good estimation from this. So now that we have an intuition of what is going to happen, let's go back to the math and try to understand this in detail. So recall that capital X is the random variable corresponding to the features, Y is the random variable corresponding to the label. Now, if I'm going to look at, so in most of the discussion, if it's a capitalized variable, it's a random variable, while if it's a small value, then it corresponds to whatever is the value at the realization that's been observed here. So what is this? It basically is the model which is built based on the observations which are small dn. This is basically the random variable corresponding to the model which is built based on the dn set of samples. And this is going to be a predictor. And this is the error between the two essentially is, and the square of the error is the mean square loss. Clearly, first thing to look at is what are all the variables here. The first variable essentially is what is that test set, sorry, what is the training set of inputs that you're going to give. The dn's are the training samples that you're going to feed in to build the model. What is the second variable here, the x and the y's, which is corresponding to the test ones, right? So the test samples are also variables, so are the train samples. So the assumption here is that if the model is going to perform well, then it has to perform well both on the train and the test sample realizations. So let's define that carefully. So the generalization error, so if we go back, it is fdn of x minus y, but if we want the error, then we have to look at the expected error across what all. This is the training part of it, right? The dn that we use to build the model is corresponding to the training part of it, and the x and y corresponding to the test sample are also drawn according to the same distribution p, but we can assume that the train and the test samples are drawn independently from the same distribution. If I just expand it and write, it is just a triple integral, first over the training samples, then over the test part. Now, in terms of the derivation, what is done? The only thing that is done is you take this square and then you expand the square by adding this dummy variable z. And clever choice of this dummy variable is all that is needed to understand what are all the possible different terms, and there's some little bits and pieces that we need to do. So the two steps here are as follows. The first time you try to use something which is similar to what an average classifier would behave like. What's an average classifier is, this is a classifier which is built based on all the possible sets of realizations or a large number of possible realizations, and you average over those. So let's call that as f dash. So if I find such a classifier, then I use that as one of the z values. Then the next time what you do essentially is, the same way as you average out classifiers, I can also average out based on the outputs. So let's call that as y bar. So the small catch between step 1 and 2 is that they're not almost identical. For the second step, we might need to do a little bit more. Like there's a conditional independence in the second step, which we might not be able to talk in detail right now. But if suppose someone was able to follow through the math and get to this point, then you can see these three parts to the actual generalization error. So let's recap. What does it say? The generalization error here is with respect to the train samples and the test samples for the mean square error. That gets split into the following terms. The first error essentially is by only looking at whatever is going to be your training samples and what is going to be the input for the test data. And this tells you the behavior between any classifier which is built based on your inputs and the average classifier which we still are going to believe that is obtainable. The second one essentially is going to be based on what would happen between the true label and what would have been the average label that you would have observed here. Understand that there is nothing which is corresponding to whatever is your DN, or there is no term which is related to the input distribution here. So this is purely something which is based on how good or bad the data is. In another sense, what we are trying to say here is, if let's say based on this, for the same set of features, if there is a large number of possible values of y, or for similar set of features, if you get different values of y, then the gap between the mean value of y for the same x and whatever is the set of all possible values of y would be too large, and that's basically the inherent noise which is there in the data. So this term essentially corresponds to the inherent noise in the data. Now, the second step essentially is what happens between the average classifier and the classifier which is based on the current realization. Now, if suppose, for example, the original scenario was as if like we had a model which was too simplistic, then almost every classifier that was built was almost identical, which means like these two would have had almost no differentiations. And this is what we call as the variance in the model, which is like the variance of the algorithm essentially. It is not the variance of the data. Here, this term which is called as the variance is corresponding to the variance in your algorithm. The last part here essentially is the term in the middle. Now, this is something that we have to understand a little carefully. The y bar corresponds to whatever is your mean value of the output. The f bar corresponds to whatever is the mean classifier. So what it tells you is, irrespective of what is the noise that is present in the data, you're trying to understand the behavior between an average classifier and what you observe on an average. And if those two are far away, then it basically tells you that the bias in the data is far away. So what it tells you is that it might more or less look like as if we are trying to fit a completely different model than what is inherently the true model in the data. So in some sense, just to recap, if the model we have is super complicated, it's really tightly fitting, then what would happen? The FDNs would be really good, but then the F bars will be slightly different, or the variance in the model would increase. So the better and tighter the fit it is, then we are increasing the variance. But what happens? The gap, so because each one of these models is almost as good, each model is almost going to behave well enough, so your gap between the expected behavior of the output and the expected classifier will keep decreasing. While on the other hand, a very simplistic model would actually have a very small value here, because most of the classifiers will be almost identical to whatever is the mean, and this term will decrease, while the other way around here, it will keep having a much higher bias. Note here that none of these are essentially going to change whatever is the inherent noise in your data. So this is some term which is data dependent, it cannot be disturbed. So at this point, let me stop the discussion and say that there are more interesting questions to understand the bias and the variance terms, and how we can actually look at tweaking an algorithm by identifying which of the three components are actually going awry in my data set or in my algorithm, and try to correct for them appropriately. So let me close it here and say thank you for your time.